A star just died in one of the universe's most violent explosions. Deep inside that cataclysm, a new object is born, so dense it defies comprehension. This is the protoneutron star, a seething heart of extreme physics, and at this very moment, a single phenomenon unfolds, one that dictates whether the explosion succeeds or fails utterly. It is called the prompt mechanism bounce. By the end of this, you will understand the cosmic trigger that forges the very elements you are made of. What determines if a dying star gives birth to a brilliant supernova or simply vanishes into a silent black hole? The answer lies in a microscopic dance of particles inside an object smaller than a city. What do you think is the most powerful force inside a collapsing star? This newborn object is a protoneutron star, the universe's ultimate pressure cooker. Think of it as the raw, seething heart of a giant star left behind after its catastrophic collapse. It is not the calm, stable neutron star it may one day become. For a few precious seconds, it exists in a state of violent transformation. It is a sphere of unimaginable density, cramming more than the mass of our entire sun into a space barely 20 kilometers across. At its birth, it is staggeringly hot, 1 trillion degrees or more, and composed of a seething soup of fundamental particles. Neutrons and protons are packed together tighter than atoms in a solid diamond. But the real key to this chaos, the ingredient that makes it all possible, is a flood of ghostly particles called neutrinos. These neutrinos are normally trapped by the incredible density, but for a brief moment they hold the power to shape the fate of the entire supernova. This is the extreme arena where the prompt mechanism bounce takes place. This unstoppable collapse begins deep within a dying star in its iron core. For millions of years, the star fought a balancing act, using nuclear fusion to push outward against the relentless crush of its own gravity. But iron is nuclear ash. It cannot be fused to release energy. So when the core fills with iron, the final energy source vanishes. In an instant, the balance shatters. With no outward pressure left to hold it up, the star's own immense weight turns inward and the core implodes. The entire core, a sphere larger than Earth, falls inward at an unbelievable speed, nearly a quarter the speed of light. Matter is compressed to densities beyond anything we can create on Earth, squeezing protons and electrons together to form a solid ball of neutrons. This collapse does not last long. The very center of the core, now impossibly dense, becomes rigid. It stiffens like a spring compressed to its absolute limit. When the outer layers of the collapsing core slam into this newly solidified heart, they cannot go any further. They hit a wall. In that single moment, the inward fall is stopped dead, and the energy has nowhere to go but back out. This is the bounce. A powerful shock wave ripples outward from the core, a titanic blast of energy sent back the way it came. For a brief, hopeful moment, it seems like this shock will tear the rest of the star apart, creating the supernova explosion. But the universe is not that simple. The outgoing shock wave immediately plows into the overwhelming avalanche of star matter that is still falling inward. This collision drains the shock's energy, and within mere milliseconds it stalls. It becomes a stationary wall, frozen in space, just outside the newborn protoneutron star. This stalled shock is the supernova's crisis point. It holds the entire future of the explosion in its hands. Can it be revived, or will it collapse inward, dooming the star to become a black hole? This bounce is the supernova's first and most critical cry for survival. It is the moment the collapsing core, having been squeezed to nuclear density, suddenly stiffens and pushes back. Think of it like a rubber ball hitting a concrete floor. The ball compresses violently, but its own internal structure fights back, making it rebound. In that stellar heart, the rebounding inner core slams into the outer layers that are still rushing inward. The collision creates a tremendous shock wave, a sudden wall of energy that punches its way back out through the star. For a brief, glorious instant, it seems like this single event will power the entire supernova explosion. But hope is often premature in the cosmos. The reality is that this initial shock, born from the pure force of the bounce, almost always fails. It travels a short distance and then stalls, like a wave losing all its strength just as it reaches the shore. The shock wave is drained of its energy by two overwhelming forces. First, it must tear apart the incoming avalanche of star matter, a process that consumes a colossal amount of power. Second, it is flooded by a torrent of neutrinos that carry away the shock's remaining heat. So the bounce creates the shock, but it cannot sustain it. This failure is the central puzzle of supernova physics. It means the star needs a second act, a revival mechanism to re-energize that stalled shock and finally unleash the explosion. The simple bounce is not enough. Something else must happen to turn that faltering wave into a true cosmic detonation. This stalled shock wave now faces a brutal and energy-draining task. As it pushes outward from the core, it smashes into the endless rain of stellar material still falling inward. This matter is not just simple gas, it is primarily composed of heavy iron nuclei, the very same atoms that spelled the star's doom. The shock wave's first job is to tear these complex iron atoms apart, breaking them down into their basic building blocks, protons and neutrons. This process, called dissociation, is like using a sledgehammer to smash a massive, intricate clock into a pile of its individual gears and springs. It takes a staggering amount of energy that is directly stolen from the shock wave's forward momentum. With each iron nucleus it shatters, the shock grows weaker and slower. It no longer has the strength to blast the overlying star into space. Instead, it stabilizes at a certain distance, becoming what scientists call an accretion shock. It is a stationary boundary, a front wherein falling matter piles up, gets heated, and slowly settles onto the surface of the waiting protoneutron star. This is the supernova's moment of perilous balance. The shock is frozen, unable to move outward to create the explosion, yet the protoneutron star beneath it continues to cool and shrink. More and more matter accumulates on this standing shock, adding to the weight that gravity is trying to pull down into a black hole. Without a new, powerful injection of energy, this delicate standoff will be broken by gravity's relentless pull. But the stalled shock is not alone in this fight. Trapped within the heart of the newborn protoneutron star are trillions of ghostly saviors. These are neutrinos. A single neutrino is a whisper of a particle, almost completely massless, carrying no electric charge. It barely interacts with normal matter, able to pass through a light year of lead as if it were empty space. Yet inside this cosmic pressure cooker, they are born in such staggering numbers that they become the dominant force. As the core collapsed, protons and electrons were squeezed together to form neutrons, and with each neutron created, a neutrino was flung out into the maelstrom. These neutrinos are now trapped not by walls, but by the sheer density of the star itself. The soup of particles is so thick that even these ghostly particles cannot immediately escape. They bounce and scatter, carrying with them the immense thermal energy of the trillion-degree core. For a few precious seconds, the protoneutron star is a glowing ball of light, but that light is not the visible light we see. It is a seething radiation of neutrinos. They hold the thermal energy of the entire collapse. The critical question now is whether these trapped ghosts can do more than just escape. Can they become the engine that reignites the failed explosion? This is where the prompt convection mechanism enters the stage, a potential hero in the supernova's dramatic story. Remember that stalled shock wave, frozen just outside the protoneutron star, and the sea of trapped neutrinos boiling beneath it. The core idea is beautifully direct. What if the incredible heat from those neutrinos could be delivered directly to the shock, giving it the power it so desperately needs to push outward? This is not a gentle process. It is a violent, rapid churning of the star's deepest layers. Think of a pot of water coming to a rolling boil. Heat at the bottom creates bubbles of hot water that are much less dense than the cooler liquid above. These bubbles rise in powerful plumes, carrying their heat upward in a chaotic convective motion. Inside the newborn protoneutron star, a similar instability is at work, but on a cosmic and unimaginably energetic scale. The driving force is a difference in lepton number. Leptons are a family of particles that includes electrons and neutrinos. In the star's inner regions, the concentration of these particles is much higher than in the outer layers. This creates a gradient, an imbalance that nature seeks to correct with violent urgency. Combined with the blistering neutrino heat, this instability triggers massive bubbles of hot, lepton-rich matter to erupt from the depths. These are not gentle bubbles, they are colossal convective updrafts, rising through hundreds of kilometers of dense star stuff in a matter of milliseconds. They act like a fleet of express elevators, bypassing the slow process of simple diffusion and rocketing energy directly from the neutrino furnace at the core up to the base of the stalled shock. This sudden, concentrated energy dump can be enough to re-energize the shock wave. It gives the stalled boundary a powerful, sustained push. If this prompt mechanism works as theorized, it can cause the shock to bounce a second time, not from core compression, but from thermal energy delivered from below. The entire supernova explosion could then be unleashed in a spectacular fireball within a few hundred milliseconds of the initial collapse. But is this theoretical engine powerful enough to overcome gravity's relentless grip on its own? The physics behind this prompt bounce is a story of heat, imbalance, and violent motion. At its core is a concept known as entropy, which in this context is simply a measure of chaos and heat within the star's matter. Just after the initial bounce, a critical situation develops right behind the stalled shock wave. The flood of neutrinos escaping from the protoneutron star's surface heats the matter in this region intensely, but the heating is not uniform. The layers of gas closest to the neutrino source get incredibly hot, while the material a bit further out remains relatively cooler. This creates a steep temperature drop, a so-called negative entropy gradient. Think of a tall building where the bottom floor is a blazing furnace and the top floor is a walk-in freezer. This arrangement is wildly unstable. Nature abhors such an extreme imbalance and will correct it with tremendous force. The hot, buoyant matter at the bottom does not slowly warm its neighbors. Instead, it erupts upward in colossal, supersonic plumes, while the colder, denser matter from above plunges downward in equally massive sheets. This is not a gentle stirring. It is a raging, convective firestorm that churns the entire region behind the shock wave. These rising plumes act like battering rams made of pure energy. They carry the neutrino heat directly to the underside of the stalled shock and slam into it, transferring their immense momentum. This concentrated assault does not gently push the shock. It delivers a powerful, explosive burst that can jump-start the shock wave, sending it racing outward again in a matter of milliseconds. This entire sequence, from the heating to the convective eruption, is the prompt mechanism in action. It is a fast and furious rescue attempt, all playing out in a blink of an eye. This stands in stark contrast to its more famous cousin, the delayed neutrino heating mechanism. That slower process relies on a gradual, seconds-long trickle of neutrino energy to slowly revive the shock, a patient but uncertain battle of attrition. The prompt mechanism is a sudden, decisive coup. It is the difference between a single, thunderous firecracker and a long, sputtering fuse. One offers the chance for an almost instant explosion, while the other gambles on a protracted struggle against gravity's endless pull. But how can we possibly test a theory about events buried deep inside an exploding star? We cannot recreate a supernova in a lab. Instead, scientists build their own stars inside the most powerful computers on Earth. These are not simple animations, they are full-scale digital universes governed by the unbreakable laws of physics. To simulate the prompt mechanism bounce, a supercomputer must perform trillions upon trillions of calculations every second. It has to solve in perfect synchrony three of the most complex problems in all of physics. The first is three-dimensional hydrodynamics, which tracks the violent, turbulent flow of stellar matter as it collapses, bounces, and churns. The second is neutrino transport, a monumental task of following the paths of countless ghostly particles as they scatter, absorb energy, and slowly leak out. The third is nuclear physics, modeling how atomic nuclei are torn apart and reassembled under forces we can only dream of creating. Bringing these three titanic processes together in one simulation is like trying to perfectly predict the exact path of every single leaf in a hurricane while simultaneously calculating the light from every raindrop. The computational challenge is almost beyond comprehension. These models reveal the convective bubbles in stunning detail. Visualizations show colossal plumes of hot matter, like fiery mushrooms, erupting from the depths and slamming into the stalled shock wave. You can watch the shock front, once frozen, suddenly ripple and bulge outward, rejuvenated by this concentrated energy dump. The entire explosion can blossom on the screen in a matter of virtual milliseconds. Yet for all their power, these digital stars are fragile. A tiny adjustment in the initial conditions, a different way of modeling how neutrinos interact, can mean the difference between a successful, brilliant explosion and a silent, tragic collapse into a black hole. Each simulation is a single data point in a vast cosmic experiment, helping us answer the ultimate question: is the prompt mechanism the universe's preferred way to ignite a supernova, or just one of many possible paths to stellar death? This chaos is the true engine of the explosion. Turbulence and convection are not gentle background processes here. They are the violent, decisive forces that take a flicker of energy and turn it into a firestorm. Inside the protoneutron star, you have a region of unimaginable density and heat, but that energy is useless if it remains trapped. It needs a delivery system, a way to transport that power from the furnace at the core directly to the stalled shock wave. This is where chaos becomes a tool. Think of stirring a cup of coffee with a spoon. A smooth, laminar flow does very little, but if you stir vigorously, you create swirling vortices and eddies that mix the entire cup rapidly. Now imagine that coffee is a nuclear fire and the spoon is the force of gravity itself. The initial collapse and bounce create a state of extreme instability, a perfect breeding ground for turbulence. Small ripples and perturbations in the fluid are not smoothed out. They are amplified exponentially by the intense pressure and density gradients. A tiny, random fluctuation can grow in milliseconds into a massive, supersonic plume of hot matter. This is not a single, orderly bubble rising. It is a frenzied churning, a storm of rising and sinking columns that violently mixes the star's interior. These turbulent motions act like a super-efficient conveyor belt, grabbing pockets of neutrino-heated gas from the depths and hurling them upward. They bypass the slow, inefficient process of simple conduction, forcing energy outward with explosive speed. Without this chaotic stirring, the heat would simply diffuse slowly, and the shock would remain starved and stalled. The turbulence takes a small asymmetry and magnifies it into a large-scale, powerful push, effectively tipping the scales in the supernova's desperate battle for survival. Could it be that this very chaos, this inherent unpredictability, is what ultimately determines the brilliant and varied fireworks we see in the cosmos? So we are left with two possible engines for the explosion, one brutally fast and the other agonizingly slow. The prompt convection mechanism is a sprint. It attempts to reignite the stalled shock in a breathtakingly short burst of activity, all within the first few hundred milliseconds after the core bounce. Its power comes from a violent, convective firestorm, a rapid churning that acts like a series of focused explosions right under the shock wave. This mechanism relies on chaos and instability to deliver a knockout punch almost immediately. In contrast, the delayed neutrino heating mechanism is a marathon. It unfolds over a much longer timescale, not milliseconds but entire seconds. In this scenario, the initial shock stalls and remains frozen for a surprisingly long time, forming a vast region of accumulation just outside the protoneutron star. Here, neutrinos slowly and steadily deposit their energy into this matter, like a gentle but persistent heat lamp warming a patch of ground. This gradual heating builds up pressure over seconds, eventually and hopefully pushing the shock outward in a slow, powerful swell. The primary driver in the prompt mechanism is the sheer force of hydrodynamic convection, the violent rising and sinking of matter. The delayed mechanism, however, is powered by the patient cumulative trickle of neutrino energy. One is a sudden coup, the other is a war of attrition. Each mechanism is thought to operate under different stellar conditions. The prompt mechanism might be the key for lower mass stars, where the densities and instabilities are just right for that instant convective revival. The delayed mechanism is often the favored model for more massive stars, where the gravitational pull is so immense that only a long, sustained push can possibly overcome it. One offers a quick, decisive victory. The other is a patient, uncertain gamble against an endless tide of falling star stuff. So which of these cosmic engines actually powers the brilliant death of a star? The answer might not be as simple as choosing one over the other. Buried within that chaotic churning is a subtle but critical imbalance, a gradient of ghostly particles that can make or break the entire explosion. This is the lepton number gradient, and it acts as a powerful hidden engine for the prompt bounce. Leptons are a family of particles that includes both electrons and neutrinos. During the star's catastrophic collapse, the core is not a uniform soup. Its deepest, most central regions are flooded with electrons and neutrinos, giving them an extremely high lepton number. The outer layers, however, have far fewer of these particles. This difference creates a steep slope, a gradient, with a lepton-rich center and a lepton-poor periphery. Nature strives to erase such imbalances, and it does so with a specific and violent form of motion called Ledoux convection. You can think of this like a layered cocktail where the bottom is filled with light, buoyant bubbles and the top is heavy syrup. The mixture is unstable, and the slightest disturbance will cause the lighter bottom layer to erupt upward in plumes. In the protoneutron star, the lepton-rich matter is that buoyant layer. It is not just hot, it is also lighter because of its high concentration of neutrinos and electrons. This double instability, driven by both heat and lepton content, triggers a far more powerful and efficient form of convection than heat alone could ever produce. Ledoux convection is the universe's supercharged stirring mechanism. It grabs entire parcels of this buoyant, lepton-loaded matter and rockets them upward through hundreds of kilometers of dense star stuff. These are not just thermal plumes, they are lepton delivery vehicles. When they finally smash into the stalled shock wave, they deliver a double punch. They transfer their immense thermal energy, but they also deposit their leptons, which further heats the region and increases the pressure explosively. This dual-action assault, driven by the lepton gradient, provides a much more potent and concentrated push than entropy-driven convection could manage on its own. It is this specific particle-based instability that gives the prompt mechanism its best chance to reignite the explosion in a decisive, brilliant flash. This hidden asymmetry is the key to unlocking the explosion. For decades, our best supernova models were trapped in a single dimension, simplifying the star into a series of perfect concentric shells. These one-dimensional simulations presented a sobering picture. In nearly every case, the shock wave would stall and never recover. The star would collapse silently into a black hole with no supernova to speak of. The universe, however, is not one-dimensional. It is a messy, turbulent, and asymmetric place. The critical flaw in those early models was the assumption of perfect spherical symmetry. They smoothed over the very chaos that makes the explosion possible. real stars spin, they have magnetic fields, and their interiors are seething with turbulent motion from the moment of collapse. These multi-dimensional effects are not minor details. They are the essential ingredients that break the deadlock. Convection, the violent churning we explored, cannot happen in a perfectly spherical, one-dimensional world. It requires at least two dimensions to form the rising plumes and sinking sheets that transport energy. Rotation adds another layer of complexity, spinning the protoneutron star and stretching these convective bubbles into spirals that can focus energy like a whirlpool. Even magnetic fields wound up by the rapid spin can channel matter into powerful jets. In a one-dimensional simulation, the stalled shock faces a uniform wall of infalling matter, a symmetric force that is impossible to overcome. But in 2 or 3 dimensions, the shock front is not a perfect sphere. It becomes a wrinkled, distorted surface. A convective plume slams into one specific region of the shock, creating a large, localized bulge. This bulge acts like a wedge, prying open a path of least resistance through the incoming rain of star stuff. The explosion does not push outward evenly in all directions at once. It begins in one place, breaking the symmetry and allowing the hot, high-pressure material to burst through. Think of trying to lift a perfectly round, heavy lid straight off a pot. The suction makes it incredibly difficult, but if you can tilt the lid just a little, breaking the seal on one side, the air rushes in and it lifts away with ease. Multi-dimensional effects are that tilt. They break the perfect, stifling symmetry of the collapse, allowing the shock to find a weakness and erupt. The prompt mechanism bounce fundamentally relies on this broken symmetry. Its violent convective plumes are a multi-dimensional phenomenon. Without at least 2 dimensions to operate in, the mechanism is crippled and the explosion fails. So the transition from one-dimensional to 3-dimensional simulations did not just add visual detail. It transformed our understanding of stellar death, revealing that it is the inherent lopsidedness and chaos of a star's final moments that ultimately grant it a brilliant rebirth. Rotation adds a powerful spin to this chaotic collapse. The dying star's core was likely already rotating, perhaps slowly at first, but as it collapses, a fundamental law of physics takes over. Just like an ice skater pulling in their arms to spin faster, the shrinking core spins up to incredible speeds. This rotation is not just a side effect, it is a transformative force. It wraps the convective plumes of the prompt mechanism into spiraling vortexes, focusing their energy like a whirlpool channeling water. This spin can turn a general churn into a more organized, powerful engine, potentially making the prompt bounce more effective. But rotation also brings a partner, one of the most formidable forces in the universe, magnetism. As the core spins faster, it drags the star's innate magnetic field lines with it, winding them up trillions of times tighter. What was once a diffuse magnetic field becomes a colossal, structured web of energy woven through the protoneutron star. In some extreme cases, this amplified magnetic field can overpower convection entirely. Instead of chaotic plumes, the field can channel the outgoing matter into 2 narrow, hypersonic jets erupting from the star's poles. This creates a drastically different kind of explosion, one that is highly directional and might be linked to gamma-ray bursts, the most luminous events we know. The outcome of this magnetic struggle directly forges the final remnant, a successful prompt convection explosion, aided by moderate rotation, likely leaves behind a typical, rapidly spinning neutron star, a pulsar. But if magnetic fields grow truly dominant, they can imprint a surface magnetic field 1,000 trillion times stronger than Earth's, creating a magnetar, a star with a magnetic field so intense it can crack the star's crust and power years of brilliant X-ray flares. The initial spin of the core, a property set long before the star died, becomes a cosmic dial. It twists the prompt mechanism, amplifies magnetic monsters, and ultimately decides the character of the stellar corpse left behind. Deep inside this newborn stellar heart, a frantic transformation is underway. the protoneutron star is less a solid object and more a seething, chaotic soup of fundamental particles, all interacting at densities and temperatures that stretch the limits of physics. It is a neutrino factory running at full, unimaginable capacity. The entire volume is packed with neutrons, protons, and electrons, all crushed together and in constant, violent collision. This is not a peaceful assembly line. It is a continuous, explosive process where particles are constantly being created, destroyed, and converted. In this extreme environment, protons and electrons are being forced together under immense pressure, merging to form new neutrons. And with every single neutron born from this merger, a brand new neutrino is also created and ejected into the frenzy. This process, known as electron capture, is happening countless trillions of times every second throughout the entire core. The result is a staggering flood of these ghostly particles, a dense radiation field that now holds the key to the star's ultimate fate. This neutrino sea does not just carry away particles, it carries away the star's very binding energy, the gravitational energy that was released when the core collapsed. Think of it as the core's thermal engine, with neutrinos acting as the primary exhaust. They are the dominant force, the particles that hold the majority of the energy in the entire system. The sheer number of them is so vast that even though an individual neutrino barely interacts, their collective presence creates an opaque fog. They bounce and scatter, trapped long enough to thermalize, to come into equilibrium with the intensely hot matter around them. This trapped sea of neutrinos is what defines the protoneutron star's structure and its evolution. It is the pressure from this neutrino radiation, pushing outward, that helps support the star against its own tremendous gravity, preventing an immediate collapse into a black hole. And it is the slow, diffusive escape of these neutrinos over several seconds that will ultimately cool the star, allowing it to condense into a stable neutron star. But in these first critical moments, the dynamics are driven by their frantic production and their desperate struggle to get out, a struggle that powers the convective engine we have been exploring. The entire system is a breathtaking balance, a cosmic dance between particle creation, energy transport, and gravitational collapse, all orchestrated by the silent, ghostly neutrino. That single, powerful plume of lepton-rich matter finally reaches the stalled shock. It slams into the shock's underside not as a gentle push, but as a supersonic battering ram of pure energy. The shock front, which had been frozen and static for tens of milliseconds, suddenly ripples. It bulges outward in one localized region, a blister of immense pressure prying open a weakness in the relentless inward rain of iron. This is the turning point. The symmetry is broken. Once one plume succeeds, others follow in a rapid cascade. The entire region behind the shock becomes a chaotic forge of rising, superheated columns and sinking, cooler rivers of matter. This violent churning acts like a thermal engine, converting the trapped neutrino heat into kinetic energy with brutal efficiency. The stalled shock is no longer stalled. It is reborn. It begins to move outward, not slowly, but in a rapid, accelerating wave. It surges through the infalling stellar layers, and this time it does not stall. The shock front is now so powerful and fast that it overtakes the collapsing material. It rips through the star's inner structure, a blistering wave of destruction traveling at tens of thousands of kilometers per second. As it moves outward, it heats the gas it passes through to billions of degrees, triggering a furious storm of new nuclear reactions. In mere seconds, the shock wave reaches the star's outer layers. The entire star, from the inside out, is now unbound. The gravitational grip of the core is shattered. The outer envelope of the star, a colossal sphere of gas, is blown into the void in the most spectacular explosion the universe can produce. A supernova is born. The energy released in this single event, driven by that initial convective punch, can outshine an entire galaxy of stars. This is the brilliant, violent death that forges the elements of life and scatters them across the cosmos. It all hinged on a chaotic engine deep within, a successful prompt bounce that turned collapse into cataclysm. But a brilliant flash of light in a distant galaxy is the final chapter of a story that began deep within a stellar corpse. So how can we possibly know if the prompt mechanism was the true hero? The answer lies not just in the light, but in the ghostly signal that arrives first. The light curve of a supernova, the graph of its brightness over time, is its autobiography. A successful prompt bounce would write a very specific story. This explosion is fast and furious, a rapid release of energy that creates an initial flash of light which is incredibly bright but also very short-lived. The light curve would rise to a sharp, narrow peak and then fade relatively quickly. It is the signature of a decisive explosion, one that did not linger or struggle. This contrasts with the light curve from a delayed explosion. That slower mechanism, a war of attrition taking many seconds, would produce a broader, more rounded peak. The light would rise more gradually and sustain its brilliance for a longer period, telling a tale of patient, accumulated energy finally breaking through. But the most crucial evidence arrives hours before the light even does. It comes in the form of the very particles that powered the engine, the neutrinos. When a supernova occurs in our galactic neighborhood, immense detectors buried deep underground like Supercomputer and in Japan will record a sudden, intense pulse of these ghostly messengers. The timing and structure of this neutrino burst is the ultimate insider report from the heart of the collapse. A successful prompt bounce would produce a neutrino signal that is sharply peaked and incredibly intense, but also very brief, perhaps lasting only a fraction of a second. It would be the unmistakable shout of a violent convective revival. A delayed mechanism, however, would stretch that neutrino signal out over many seconds, a long, drawn-out sigh as energy slowly leaks out to reheat the shock. Future observatories like the planned Hypercamiocan will have the sensitivity to read these subtle differences in the neutrino signal like a detailed medical chart. They could distinguish the rapid, decisive heartbeat of the prompt mechanism from the slower, steadier pulse of the delayed mechanism. By matching a sharp neutrino pulse with a fast-rising light curve, we could finally have direct, multi-messenger proof of which cosmic engine is at work. We would move from theoretical models to confirmed observation, truly understanding the final thoughts of a dying star. This brilliant detonation is far more than a cosmic light show. It is the universe's ultimate forge, and the success of the prompt mechanism is what allows the anvil to ring. Deep within the expanding shock wave, a frantic alchemy unfolds. The supernova's interior becomes a nuclear furnace hotter and denser than the star's core ever was during its life. Here, the very elements that make up our world are born in a matter of seconds. The flood of neutrons from the explosion slams into atomic nuclei, building them up piece by piece in a furious process called the rapid neutron capture process. This is how elements heavier than iron, like silver, gold, and uranium, are created. Without the violent, outward thrust of a successful explosion, these newly forged elements would simply fall back into the gravitational well of the collapsed core, vanishing forever into a black hole. The prompt mechanism bounce is the crucial trigger that prevents this cosmic tragedy. It is the difference between a sealed tomb and an open doorway. When the shock wave succeeds, it does not just blow the star apart. It catapults this newly created elemental treasure trove out into the void at incredible speeds. Clouds of gas enriched with oxygen, carbon, silicon, and iron are flung across light years, mixing with the pristine hydrogen and helium of the interstellar medium. This stellar debris is the raw material for everything to come. Every rocky planet, every mountain, every breath of air you take was once forged in such an explosion. The iron in your blood, the calcium in your bones, the oxygen that fills your lungs, all of it was cooked in the heart of a dying star and scattered by the force of its final triumphant blast. So the next time you look up at the night sky, remember that we are all, quite literally, the children of supernova. The very atoms that form our bodies were created in these catastrophic events, and the prompt mechanism bounce is the pivotal moment that set them free to eventually coalesce into our world and us. Yet for all its potential, the prompt mechanism is not a guarantee. Sometimes, even this violent engine of convection is not enough. The stalled shock remains frozen, and the protoneutron star beneath it continues its grim work. It acts as a gravitational sinkhole, relentlessly pulling in the endless rain of stellar debris. With every passing millisecond, more matter piles onto its surface, adding to its already immense weight. The protoneutron star is caught in a terrible race. It is trying to cool and condense by emitting neutrinos, but the accretion of new material from the dying star is happening even faster. The inward flow of matter simply overwhelms the star's ability to push it back. The pressure at the very center of this newborn object climbs to values that defy physics. The neutrons and protons, which were just barely holding their ground, are now pressed beyond their absolute limit. There is a fundamental boundary in our universe, a point of no return known as the Tolman-Oppenheimer-Volkoff limit. This is the maximum possible mass a ball of neutrons can support before gravity wins the final battle. For a protoneutron star, this limit is not a fixed number. It is a shifting threshold influenced by its temperature, rotation, and composition. But as it accretes more and more mass, it inevitably crosses that line. The internal pressure from neutron degeneracy, the very force that was holding the star up, suddenly vanishes. It is as if the floor of the universe simply gives way. In less than a single second, the entire structure catastrophically fails. The protoneutron star, an object containing 2, 3, or even 4 times the mass of our Sun, collapses completely. Its boundary shrinks past the point where even light can escape. A new event horizon forms, a silent and perfect black sphere in space. From the outside, the result is profoundly anticlimactic. The entire region simply vanishes. The infalling matter, which moments before was crashing onto a hot, dense surface, now crosses an invisible threshold and winks out of existence. There is no second shock wave, no brilliant explosion, no scattering of newly forged elements. The star's outer layers, deprived of the rebounding push they desperately needed, continue their unimpeded fall directly into the newly formed black hole. The star dies not with a bang, but with a whisper, leaving behind only darkness and gravity. This silent fate might be the most common end for the very heaviest stars, those titans whose cores are so massive that no conceivable mechanism can overcome their gravitational pull. Their death creates a legacy not of light and life, but of ultimate shadow. Just when we think we understand the rules, the neutrino changes the game. These ghostly particles have a secret identity crisis. They are not one single, stable type. Instead, they exist in 3 distinct flavors: the electron neutrino, the muon neutrino, and the tau neutrino. And as they travel, they spontaneously morph from one flavor into another in a bizarre quantum process called oscillation. This is not just a curious detail. In the frantic environment around the protoneutron star, these oscillations can dramatically reshape the entire energy landscape of the explosion. Think of the neutrinos as different types of specialized fuel. Electron neutrinos are deeply involved in the nuclear reactions that create neutrons, while muon and tau neutrinos interact with matter in subtly different ways. In the empty vacuum of space, these oscillations happen over long distances. But inside the supernova, the density is so immense that it fundamentally alters the oscillation process. The presence of countless other electrons and neutrinos creates a refractive medium, bending the probabilities of these transformations in strange and unpredictable ways. This means the flavor of a neutrino escaping the core is not necessarily the flavor it had when it was born. A crucial electron neutrino, perfectly tuned to deposit its energy in the right place to heat the shock, might transform into a muon neutrino just before it arrives, an actor changing its costume right before stepping on stage. This transformation changes how effectively that neutrino can dump its energy into the stalled shock. If the wrong flavors dominate in the heating region, the entire revival mechanism can become less efficient, like a fire being fed with damp wood instead of dry kindling. The delicate balance of the prompt convection, which relies on a precise delivery of heat, is now subject to the whims of quantum probability. This adds a staggering layer of complexity to our supercomputer models. Scientists must now track not just the energy and direction of trillions of neutrinos, but also their ever-shifting quantum identities. It turns the already difficult problem of simulating a supernova into a three-dimensional, multi-flavor quantum mechanical puzzle. The success or failure of the prompt bounce may ultimately depend on this hidden dance of identities happening at the smallest scales imaginable. The frontier of supernova research is now a digital one, where international teams race to simulate a star's death in ever more exquisite detail. Groups like the Garching Group in Germany and the Oak Ridge team in the United States are pushing the boundaries, running three-dimensional models on the world's most powerful exascale computers. These are not just prettier visuals, they are revolutionary tools that incorporate the full chaos of magnetic fields, precise neutrino transport, and the strange quantum dance of neutrino oscillations. Their latest simulations reveal a universe more nuanced than we ever imagined. The prompt mechanism does indeed work, but it is not a universal key. It appears to be a viable engine, but its success depends on a delicate and precise recipe of initial conditions. The open questions are now sharper than ever. How common is this rapid explosion? It might be the dominant mechanism for lower mass stars, while its delayed cousin takes over for the true giants of the cosmos. What are the precise ingredients that favor the prompt bounce? The initial spin rate, the exact structure of the iron core, and the strength of pre-collapse turbulence in the star's final hours all appear to be critical factors. A tiny change in any one can tip the balance from a brilliant explosion to a silent collapse, but the most pressing question is one of confirmation. How do we move from seeing these explosions in our computers to definitively identifying them in the sky? The answer lies in the next generation of neutrino detectors and space telescopes, instruments that will catch the unique fingerprint of a prompt bounce, that sharp, intense neutrino pulse followed by a fast-rising light curve. We are on the verge of not just modeling these events, but of truly reading the final moments of a star's life, directly from its last breath of light and its first whisper of ghosts. The final, violent act of the explosion imprints its signature directly onto the newborn neutron star. How the shock wave revives, whether through a prompt, convective coup or a slower, delayed struggle, dictates the very first moments of this stellar corpse's life. Think of the explosion not as a perfectly spherical blast, but as a lopsided eruption. The prompt mechanism, with its chaotic, rising plumes, is inherently uneven. One side of the shock wave might be pushed outward with more force than the other. This asymmetry is the engine that gives neutron stars their incredible kick velocities. As the explosion debris rockets away in one direction, the neutron star itself recoils in the opposite direction, just like a cannon firing a cannonball. The newborn star is shot out of its cradle at hundreds of kilometers per second, a speed so great it can escape its own galaxy. The character of the bounce also determines the star's spin. A core with even a modest amount of rotation will see that spin amplified dramatically during the collapse. If the prompt convection is vigorous, its turbulent plumes can act like a chaotic hand, grabbing onto that spin and accelerating it further. The result is a pulsar, a neutron star born spinning hundreds of times per second, its lighthouse beam of radiation sweeping across the cosmos. The magnetic field, too, is forged in this crucible. The same convective motions that power the explosion stretch and wrap the star's innate magnetic field, amplifying it to almost unimaginable intensities. A successful prompt bounce could create a typical pulsar, but a slightly different balance of convection and rotation might twist that magnetic field into a structure 1,000 trillion times stronger than Earth's, birthing a magnetar. So the microphysics of the bounce, the specific dance of particles and plumes deep within the core, does not just cause an explosion. It sculpts the final remnant, setting its speed, its spin, and its magnetic personality for the rest of its existence. This cosmic forge is also a powerful engine for innovation right here on Earth. The same computational tools we use to tear apart a star are now helping us build a better future. To simulate a supernova, scientists had to invent entirely new ways of solving impossible problems, creating algorithms that can handle unimaginably complex systems. These breakthroughs in computational fluid dynamics did not stay locked in an astrophysics lab. They have spun off into technologies that touch your life every single day. The equations that track the chaotic flow of plasma inside an exploding star are the very same ones that help engineers design more efficient jet engines, allowing for cleaner and quieter air travel. The methods developed to untangle the paths of trillions of neutrinos have revolutionized how we analyze massive datasets, from predicting global weather patterns to optimizing national power grids. Even the medical field has been transformed. The sophisticated image reconstruction techniques used to visualize the three-dimensional violence inside a supernova core are directly applied to modern medical scanners. When you get an MRI, the machine uses computational principles born from stellar collapse to peer non-invasively into the human body, creating exquisitely detailed images that help diagnose disease and save lives. But the connections run even deeper than data processing. The protoneutron star is a natural laboratory for matter under conditions we cannot hope to recreate on our planet. By studying how nuclear particles behave at these extreme densities, we are essentially reading the universe's own blueprint for high-energy physics. This fundamental knowledge is critical for the next generation of energy technology. It informs the quest for nuclear fusion, helping us understand how to confine and control a superhot plasma to one day harness a star's power here on Earth. The challenges of simulating quantum neutrino oscillations are pushing the boundaries of quantum computing itself, accelerating the development of machines that could solve problems in medicine, chemistry, and logistics that are currently beyond our reach. So the death of a distant star is not just a spectacle, it is a catalyst. The struggle to understand the prompt mechanism bounce forces us to develop new tools, and those tools in turn reshape our world. The ultimate legacy of a supernova is not only the iron in your blood or the gold in a ring, but also the invisible architecture of the advanced technological society you live in. This ultimate test is coming, and it will be a symphony of cosmic messengers. For the first time in history, we are building the tools to observe a supernova not just with light, but with every sense at our disposal. The next time a massive star dies in our galactic neighborhood, an alarm will ripple across the global scientific community. It will begin with a silent shout, a sudden burst of neutrinos washing over the Earth. Deep underground, detectors like supercamioc and the future hypercamioc and will register this ghostly pulse, pinpointing the direction of the collapse hours before the star's outer layers have even begun to brighten. Minutes later, a new kind of tremor will be sensed. Gigantic laser interferometers like LIGO, Virgo, and CAGRA will feel the faint, rippling distortion in spacetime itself. These gravitational waves are the direct signature of the core's violent bounce and the frantic churning of the protoneutron star, a fingerprint of the explosion engine's mechanics. Finally, as the shock wave tears the star apart, telescopes across the globe and in space will turn to witness the brilliant flash of light, the traditional supernova we have watched for centuries. But now, that light will be just one instrument in a grand orchestra. by correlating the precise timing, energy, and structure of the neutrino burst with the gravitational wave signal and the unfolding light curve, we will have a complete multi-messenger autopsy of the star's death. The data will be undeniable. A sharp, split-second neutrino pulse coupled with a specific gravitational wave chirp would be the smoking gun for a successful prompt convection bounce. A longer, drawn-out neutrino signal with a different waveform would clearly signal the delayed mechanism at work. This is not a distant dream. It is the imminent future of multi-messenger astronomy. We are now laying the groundwork for that single, transformative event, an explosion close enough to read in perfect detail. When it happens, the decades of theoretical debate and computer modeling will converge on one set of observations, finally revealing the true trigger behind one of the universe's most magnificent and creative acts. From a silent collapse to a universe-altering detonation, this entire journey hinges on a single, chaotic bounce. We began with a star's iron heart failing, leading to an implosion so violent it forged a protoneutron star. We witnessed the birth and stalling of a shock wave, a supernova in crisis, and we explored the frantic rescue attempt, the prompt mechanism bounce, where violent convection and a sea of ghostly neutrinos struggle to reignite the explosion. This phenomenon is more than just physics, it is a potential cosmic trigger. When it succeeds, it is the event that forges the elements of life and scatters them across the galaxy, ensuring that stellar death is not an end but a brilliant new beginning. These hidden engines operating in the hearts of dying stars are the reason we exist, so the next time you gaze at the stars, remember the incredible forces at work in the darkness, the silent dances of particles and pressure that shape our cosmos. Stay curious and keep looking up. The universe is full of stories waiting to be told. Now, we would love to hear from you. What part of this incredible journey fascinates you the most? Is it the sheer density of a neutron star, the ghostly power of neutrinos, or the chaotic beauty of the convective plumes? Share your thoughts in the comments below.